criteria. The first one is based on output waveform. It can be classified into square waveform, sinusoidal waveform, triangular waveform generator. So next one is based on feedback components. It can be classified into RC oscillator, LC oscillator, crystal oscillator. Example for this RC oscillator, RC phase shift oscillator, Wein bridge oscillator. So LC oscillator is classified into Hartley Oscillator, Colpitt's Oscillator and Clap Oscillator. Crystal Oscillator is classified into Quartz Crystal Oscillator, Pierce Crystal Oscillator and Miller Crystal Oscillator. The next type is based on mechanism used. It can be classified into two types, negative resistance oscillator, feedback oscillator. The example for this feedback oscillator is UJT relaxation oscillator, that is very important one, in which no feedback is used. Okay. The last one is based on frequency range. It can be classified into 5 types. The first one is AFO, audio frequency oscillator. It ranges from 20 Hz to 20 kHz. Next one is RFO, radio frequency oscillator. It ranges from 20 kHz to 20 MHz. Very high frequency oscillator, 30 MHz to 300 MHz. Ultra high frequency oscillator, 300 MHz to 3 GHz. The last one is microwave oscillator, which is greater than 3 GHz. Okay, so this is the overview of the types of the basics of oscillator. Let's start with the definition. It is an electronic circuit which can self-generate the waveform without any input. So without any input means, consider this is the oscillator device. We are not going to give any input. We are going to simply give the DC supply voltage which is required for the operation of an active device used in this electronic circuit. So in this oscillator we are using transistor as an electronic device. For the transistor we can give DC supply voltage. This is not that input voltage. Okay. So without any input signal it can generate the output signal. It is basically an amplifier circuit with positive feedback with feedback components like RC, LC or crystal circuits. In this circuit, there is no input signal given to this amplifier. Okay. So here the amplifier consists of an active device. It can be either BJT, FET or op-amp. Okay. So here the active device requires DC supply voltage for its operation. So we are giving only the DC supply voltage to this amplifier, not the input. Okay, it can generate some small amount of noisy signal as the output that can be given as input to this feedback with a gain beta. It can produce the feedback signal VF. So for this oscillator, the input signal is nothing but the feedback signal. Do you all understand? There is no actual input. This feedback can also be taken from the output signal from this amplifier. Do you all understand this concept? That's what given here. Okay, so we are not giving any input signal. We are simply giving the DC supply voltage which is required for the operation of active devices used in this electronic circuit. Do you all understand this concept? So oscillator is basically an amplifier circuit with positive feedback. The gain of the positive feedback is AF is equal to A by 1 minus A beta. So the next one is condition for oscillation or Barkasian criterion. This is very important. There are two conditions. So the first one is the magnitude of A beta is equal to 1. So here A beta is nothing but the loop gain of the system. Loop gain means the product of amplifier gain and the feedback gain. So here the magnitude of A beta is equal to unity. That is the first condition. The next one is the total phase shift around a closed loop is 0 degree or 360 degree. So in another term we can say integral multiple of 2 pi radians. So whichever circuits satisfy these two conditions can be used as oscillators. Do you all understand this? A beta is equal to 1. Total phase shift is 0 degree or 360 degree. It is also known as Barkhasan criterion. Next one is specification of oscillator. So whenever we are going to select an oscillator, we have to consider some specific parameters. Those are given here. Frequency stability, output frequency, allowable waveform distortion, range of frequency tuning circuit and output power. So we have to consider all the specifications for our applications. Okay. So the last one is applications of oscillator. It is widely used in watches, especially quartz crystal oscillators. Okay. It is used in watches, audio systems and video systems. It is used in communication devices like TV, radio, etc. It is also used in computers, radio circuits, smartphones, ultrasonic devices, metal detectors, etc. Microwave oscillator is condition for oscillation that is also known as Barkhasan criterion. There are two important conditions to be used in oscillator circuits. Whichever electronic circuits satisfy these two conditions, those can be used as oscillators. Okay. The first condition is modulus of A beta is equal to 1. That is the magnitude of loop gain A beta is equal to unity. The second condition is total phase shift around the closed loop is either 0 degree or 360 degree. Do you all understand? So in this video, we are going to prove these two conditions for oscillator circuits. So for that, we can consider an inverting amplifier with open loop gain A. This is the basic inverting amplifier circuit. So in which we have to give the input signal Vi and we can get the output signal as A into Vi. 180 degree phase shift. So you can see this 180 degree phase shift in this waveform. So here it starts from positive, here it starts from negative. So this is the basic inverting amplifier. So we are going to use this inverting amplifier in our oscillator circuit. This is the basic oscillator circuit. It consists of basic inverting amplifier with gain A and a positive feedback with gain beta. There is no input given to this circuit. Here we can get the output voltage from this amplifier due to the DC supply voltage, not from this input signal. Okay. This output signal is given as input to this feedback. Then we can get the feedback signal as VF that is given as an input to this basic inverting amplifier. Do you all understand this concept? So feedback signal drives the amplifier circuit. So here inverting amplifier produces 180 degree phase shift. So if we are going to give input signal, here we can assume there is a fictitious input signal. Fictitious means what? We can imagine there is an input signal which starts from positive. So obviously we can get the 180 degree phase shifted output as VO. So it starts from negative side. Then that can be taken as input to this feedback. So this positive feedback gives 180 degree phase shift to make the feedback signal in phase with the input signal. Do you all understand this concept? So totally there are 360 degree. So one is from inverting amplifier, another one is from positive feedback. So the first condition of Barkhasan criterion is achieved. So next one. So if the feedback is adjusted so that the loop gain A beta is equal to 1. Do you all understand this diagram? So this is the simplified diagram here. Here we are not giving any input signal. This feedback signal drives the amplifier. Okay. So here we can consider a fictitious voltage Vi applied at the input of the amplifier. Actually it is an imaginary one. We can assume there is a input voltage. Okay. So here gain of the amplifier is A, that is equal to output voltage by input voltage. From this we can get VO is equal to A into Vi. Consider this as the first equation. The feedback factor beta decides the input to be given to the amplifier. Okay. So here Vf is equal to what? Minus beta into VO. As we know that beta, that is the gain of the feedback network, that is equal to output to that input. So here input is VO, output is VF. This minus sign indicates there is a 180-degree phase shift due to positive feedback. So from this we can get VF is equal to minus beta VO. Consider this as the second equation. So next we are going to substitute this first equation in the second equation. This VO can be replaced with the value A into Vi. Then we can get Vf is equal to minus beta into A into Vi. We can write that equation as Vf is equal to minus A beta into Vi. Consider that as the third equation. For oscillator circuits, the feedback signal is given as input to the amplifier. Correct? Feedback is nothing but the input to the amplifier. So we can say Vf is equal to Vi for an oscillator circuit. Then the third equation can be written as Vi is equal to minus A beta into Vi. Then we can cancel these two values, right? We can get the answer as minus A beta is equal to 1. This is called as Barkasian criteria. So it is in rectangular form, that is A beta is equal to minus 1 plus J0. The imaginary part is 0 here. If we are going to take the magnitude for this loop gain, we can get modulus of A beta is equal to 1. Okay. Thus the magnitude of loop gain is unity. The first condition is obtained. Okay. Next we have to prove the total phase shift required for this oscillation. So here the total phase shift around the closed loop is equal to the sum of phase shift introduced by inverting amplifier and the phase shift produced by the positive feedback. Correct? That is given as total phase shift around the closed loop is equal to 180-degree phase shift by inverting amplifier plus 180-degree phase shift by positive feedback. Here we can get total phase shift is equal to 360-degree. Thus the total phase shift around the loop is either 0-degree or 360-degree. It can also be mentioned like this, that is integral multiple of 2 pi radians. Okay. In these two conditions, the circuit works as an oscillator producing the sustained oscillation. Sustained oscillations means with constant frequency and constant amplitude. Okay. So next we are going to discuss the types of oscillations due to the A beta value. So we can say based on the magnitude of A beta, there are 3 types of oscillations. Okay. That is also known as the effect of A beta on the nature of oscillation. So first one is modulus of A beta is greater than 1. What will happen? So when the total phase shift around the closed loop is 360-degree or 0-degree, that first condition is okay. Here the next condition is greater than 1. In that case, the growing type of oscillations are produced. Do you all understand? Growing means it is exponentially increasing its amplitude. So it can generate the signal, but its amplitude is exponentially increased. Second case, when the total phase shift is 360-degree or 0-degree, but the magnitude of A beta is less than 1, then it can produce the oscillations with decaying type. That means the amplitude of the signal is getting decreased exponentially. Okay, for A beta is less than 1, decaying type of oscillations are produced. Okay, then the last one, if A beta is equal to 1, that is the exact condition of Barkasian criterion. So when the total phase shift around the loop is 0 degree or 360 degree and A beta is equal to 1, then the sustained oscillations are produced with constant frequency and constant amplitude. So this is what we require for signal generation. Okay. Discuss Hartley oscillator and its operation in detail. Hartley oscillator is a type of LC oscillator which uses two inductors and one capacitor in its feedback network. So next, construction of Hartley oscillator. It has two stages, amplifier stage, feedback stage. The amplifier uses an active device, that is a transistor, in common emitter configuration. The common emitter configuration produces 180 degree phase shift between the input and output. R1, R2 and RE, these resistors are used to provide the proper DC bias to this transistor. Okay, there are coupling capacitors CC1 and CC2 at the input side and output side. So this is that amplifier circuit using transistor. So the next one is feedback network. It consists of two inductors L1 and L2 and one capacitor. This feedback network determines the frequency of oscillation. Okay, so next we are going to analyze the operation. So here, when the supply voltage is given to this amplifier, the capacitor starts charging. So when the capacitor is fully charged, it starts to discharge through this L1 and L2. So here we have to consider these three terminals, terminal 1, 2 and 3. This third terminal is grounded. That means at this point its potential is 0. If terminal 1 is positive, then the terminal 2 becomes negative with respect to this third terminal. Okay. So here with respect to this ground, we can say if it is plus means this becomes negative. If it is positive, it becomes negative. So here we can introduce 180 degree phase shift between the input of this feedback network and the output side. Do you all understand this? So this feedback network introduces additional 180 degree phase shift which is required for oscillation. Do you all understand this? Here the output VO is given as input at this terminal 2. So here this voltage is available across this L2 inductor and the feedback voltage is available across the inductor L1. Do you all understand this concept? So it can produce oscillatory output. Therefore, the phase difference between the terminals 1 and 2 is 180 degree. So this amplifier introduces 180 degree and here the feedback introduces another 180 degree phase shift. Totally we can have 360 degree phase shift around this loop. So that is the required condition for oscillation. So we have achieved 360 degree phase shift in this Hartley oscillator. That's what given here. The amplifier stage uses an active device as a transistor in common emitter configuration. R1, R2 are the biasing resistances to provide the DC bias to the transistor. Feedback network consists of two inductors, one capacitor, and this will decide the frequency of oscillation. This is the overview of the operation. When the supply voltage VCC is given to the amplifier circuit, the capacitor starts charging. When the capacitor is fully charged, it starts to discharge through L1 and L2. Hence, it produces oscillations with certain frequency. In a feedback network, the portion of the output voltage appears across L2 and the feedback voltage across L1. That I told you, right? So here the phase shift. How do we achieve the phase shift? Due to the feedback concept. Here the terminal 3 is grounded. That means 0 potential. If terminal 1 is at positive potential and terminal 2 is at negative potential, then we can get 180 degree phase difference between terminal 1 and 2. So in CE configuration, the transistor provides phase shift of 180 degree between input and output. Therefore, we can get the total phase shift as 360 degree.
As a college student, tech skills கற்றுக்கணும் ஆனால்
Based on the Barkashan criterion, we have to achieve the loop gain A beta as 1. For that, we have to adjust the values of feedback components to get A beta is equal to 1. So next, equivalent circuit of Hartley oscillator. In this, the transistor is represented using hybrid model. Here input impedance is HIE, the output is HFE IB, the collector resistance is RC. Across that we can take that output voltage VO. In the feedback network, we have to give this output voltage to this L2. Correct? The second inductor, and we have to take the feedback voltage across this L1. This is the overall equivalent circuit. From this we can get the simplified equivalent circuit. In this case, we have to take this output this side. So we have to consider that feedback network here is actually V0 that is given as input to this feedback network across this L2. Okay, then we can get the feedback voltage from this L1 and given as input to the amplifier. Next, we are going to derive the frequency of oscillation in Hartley oscillator. For that, we can consider the general equation for the LC oscillator. So, this is the general equation which has been already derived. This is common for any types of LC oscillator. HIE into Z1 plus Z2 plus Z3 plus Z1 Z2 into 1 plus HFE plus Z1 Z3 is equal to 0. Consider this as the first equation. So, you have to remember this general equation for LC oscillators. In case of Hartley oscillator, we have to substitute the values of Z1, Z2 and Z3. Here Z1 and Z2 are inductive reactances. Z3 is capacitive reactance. So here we can mention the values like this. Z1 is equal to j omega L1, Z2 is equal to j omega L2, Z3 is equal to 1 by j omega C. So here capacitive reactance is always denoted in the denominator. So here it is 1 by j omega C. We have to substitute all these three values in this first equation. Then we can get HIE, Z1 is j omega L1 plus j omega L2 plus 1 by j omega C plus Z1 Z2, right? So here j omega L1 into j omega L2 into 1 plus HFE. Here it is plus Z1 value is j omega L1, Z3 value is 1 by j omega C. That is equal to 0. So next we have to simplify these values here. So next HIE j omega L1 plus j omega L2. Here we can have j omega as a common term for this 2. But here it is in the denominator. So we have to multiply the numerator and denominator with the value j omega. So here it becomes j omega divided by j squared omega squared C plus this side j squared omega squared L1 L2 into 1 plus HFE. Here j omega divided. Then we can get L1 by C is equal to 0. Okay, so in the next step, we have to take this j omega as a common term from this bracket. We can get HIE j omega into L1 plus L2 minus this 1 by j squared. So 1 by j squared means it is minus 1. J squared is always minus 1, right? So we can say minus 1 by omega squared C minus, here j squared is nothing but minus 1. So minus omega squared L1 L2 into 1 plus HFE plus L1 by C, that is equal to 0. So now we have obtained the general equation for Hartley oscillator. So here it is having real part and imaginary part. So this is what the real terms, okay, which is not having any j term. So the j term is known as imaginary part, okay. We can simply rewrite the above equation as L1 by C minus omega squared L1 L2 into 1 plus HFE, that is the real term, plus imaginary term j omega HIE L1 plus L2 minus 1 by omega squared C, that is equal to 0. Consider this as the second equation. So this is the general equation of Hartley oscillator. we have derived this general equation especially for this Hartley oscillator. Next, we are going to find out the frequency of oscillation. So here, we know that at resonant frequency condition, so at resonant frequency condition, the reactance values both are equal. That is XL is equal to XC. So if you want to find out the frequency of oscillation is nothing but resonant frequency. So at this frequency, the reactances can be cancelled each other to give the imaginary part as 0. So in order to determine the frequency of oscillation at resonant condition, the imaginary part of this second equation is equal to 0. So what is the imaginary value? Omega HIE L1 plus L2 minus 1 by omega squared C. We can take that value and make it as equal to 0. Then we have to move this omega HIE to this side as a denominator. 0 divided by anything becomes 0. Correct? Then we can have L1 plus L2 minus 1 by omega squared C is equal to 0. Then we have to move this 1 by omega squared C to this side as a plus 1. So we can get L1 plus L2 is equal to 1 by omega squared C. Then we have to move this omega squared C to this side as a numerator and move this L1 plus L2 to this side as a denominator, because we are going to find out the value of frequency. Okay. So omega squared C is equal to 1 by L1 plus L2. Then we have to move this C to this side as a denominator. Then we can get omega squared is equal to 1 by C into L1 plus L2. Consider this as the third equation, because we are going to use this equation in the next derivation part. Okay. So omega squared is equal to what? 1 by C into L1 plus L2. Then we have to take the square root on both sides. We can get omega is equal to 1 by square root of C into L1 plus L2. Here omega is nothing but 2 pi f. So from this we can get this f value by moving this 2 pi to this side as a denominator value. We can get the frequency of oscillation for Hartley oscillator is f is equal to 1 by 2 pi square root of C into L equivalent. L equivalent is nothing but what? L1 plus L2. So this is very important formula. We are going to use these formulas to solve some problems in the next video lecture. Okay. Next we are going to derive the condition for oscillation in Hartley oscillator. In order to determine the condition for oscillation, the real part of the equation 2 is equated to 0. Condition for oscillation, that means we are going to find out the gain. Okay, gain of the transistor. This will decide the oscillation in Hartley oscillator. For this we have to consider the real part as 0. Okay. So here real part is what? L1 by C minus omega square L1 L2 into 1 plus HFE is equal to 0. Then we have to move this minus side to this side as a plus 1. So next we are going to substitute the third equation in this equation. So what is the third equation? That is omega square. Its value is 1 by C into L1 plus L2. Okay, this omega squared is replaced with this value, and this here it is L1 L2 into 1 plus HFE. Okay, then we can divide these two values, okay, on both the sides. Then this side becomes 1, that is equal to L2 into 1 plus HFE divided by L1 plus L2. So next step, we are going to keep this 1 plus HFE here and move this term, okay, to this side in a reciprocal manner. Moving this side, then we can get 1 plus HFE is equal to, this L2 is common for both the terms, that is L1 by L2 plus L2 by L2. So this term becomes 1. So 1 plus L1 by L2, this 1 and 1 cancel each other. Then we can get HFE is equal to L1 by L2, where this HFE is nothing but forward gain of the transistor. Okay, this HFE is nothing but what? Forward gain of the transistor using hybrid model. Hartley oscillator, for getting an oscillations, the forward gain of the transistor is always greater than or equal to L1 by L2. This is also important formula to use this to solve some problems. Okay. Finally, in practical case, L1 and L2 are wound in a single core. In case of single core, it can experience the mutual inductance between L1 and L2. Hence, the formula of the L equivalent becomes L1 plus L2 plus 2M. So, here M is nothing but mutual inductance between L1 and L2. Here, the frequency of oscillation is equal to 1 by 2 pi square root of C into L1 plus L2 plus 2M. And also, the forward HFE is equal to L